If I place these two objects in front of you, a perfectly cut diamond, and this ugly, burned-looking rock, which one would you choose? Most people would choose the diamond. A planetary geologist might choose the rock, because this ordinary-looking stone could be worth tens of thousands of dollars. In some cases, even millions. And when scientists cut certain meteorites open, this is what they discover. Metallic crystal structures, ancient mineral textures, patterns that took millions of years to form, structures that cannot be naturally reproduced anywhere on Earth. This isn't simply a rock, it's a surviving fragment of another world. In April 2023, fragments of Maine's first officially confirmed meteorite sold for more than $25,000 each. The famous Fukang meteorite, discovered in China in 2000, became one of the most valuable palisite meteorites ever found, with some specimens valued at millions of dollars. And perhaps the most remarkable fact is this: nobody mined these objects, nobody manufactured them, they simply fell from the sky. Every year, thousands of people walk past unusual rocks. Most are ordinary terrestrial stones, but occasionally one turns out to be a genuine meteorite, a physical sample of the earliest solar system, a geological artifact older than Earth itself. And if you understand the clues geologists look for, you might recognize one. Today, we're going to investigate what meteorites actually are, where they come from, and why scientists consider them some of the most important geological specimens on Earth. To understand meteorites, we need to travel back approximately 4.6 billion years. Before Earth, before the Moon, before the planets existed. At that time, our solar system consisted of a vast cloud of gas, dust, metals, and microscopic mineral particles orbiting a young sun. Over millions of years, gravity caused these particles to collide. Some collisions created larger bodies. Eventually, planets formed. But not every object became a planet. Many remained relatively unchanged. Today, we know these ancient survivors as asteroids. Most meteorites originate in the asteroid belt located between Mars and Jupiter. This region contains millions of rocky and metallic bodies. For billions of years, these objects have collided with one another. Each collision produces fragments. Most remain trapped in space. But occasionally, gravitational disturbances alter their trajectories. Some begin journeys lasting millions of years, and a few eventually collide with Earth. As these objects enter Earth's atmosphere, they travel at tremendous speeds. Compression and friction generate enormous heat. Many objects vaporize completely, others survive. Those survivors become meteorites. And every meteorite that reaches Earth carries information from a time before our planet existed. Not all meteorites come from asteroids. Some come from Mars. Others originate from the Moon. Scientists confirm this by comparing trapped gases found inside meteorites with samples collected during space missions. The chemical signatures matched. This discovery fundamentally changed planetary science, because it meant that some rocks found on Earth are literally pieces of other worlds. These meteorites are among the rarest geological specimens ever discovered. Meteorites are generally divided into three major categories. Each preserves a different chapter of solar system history. The first category is stony meteorites. These account for approximately 95% of all meteorite falls. The most common type is known as a chondrite. Notice these tiny spherical structures. These are called chondrules. They formed approximately 4.56 billion years ago during the earliest stages of solar system formation. To planetary scientists, chondrites are geological time capsules. They preserve chemical information from before the planets formed. Another type of stony meteorite is called an achondrite. Unlike chondrites, these meteorites formed inside bodies that experienced melting and volcanic activity. Some chondrites have been traced directly to Mars. Others originated on the Moon. When scientists analyze these rocks, they are effectively studying extraterrestrial geology without leaving Earth. The second major category consists of iron meteorites. These meteorites are composed primarily of iron and nickel. Scientists believe they originated deep inside ancient planetary cores. Billions of years ago, some asteroids became large enough to separate into layers. Heavy metals sank toward the center. Rocky material remained above. Later, catastrophic collisions shattered these worlds apart. Fragments of their metallic cores escaped into space. Some eventually landed here. When iron meteorites are polished and chemically etched, they reveal one of the most extraordinary structures in geology: the Widmanstätten pattern. This interlocking crystal structure formed through cooling processes that occurred over millions of years. No naturally occurring Earth rock produces this exact pattern. For meteorite scientists, its presence is among the strongest indicators of extraterrestrial origin. The rarest category of all is known as stony iron meteorites, and among them the most spectacular are pallasites. These meteorites contain transparent olivine crystals suspended within metallic iron. Olivine belongs to the same mineral family as the gemstone peridot. Scientists believe pallasites formed at the boundary between the metallic core and rocky mantle of ancient planetary bodies. In other words, they preserve environments that no longer exist anywhere in our solar system. Their beauty makes them valuable. Their rarity makes them extraordinary. Their scientific importance makes them priceless. But this raises an important question. If meteorites really do fall onto Earth every year, how can an ordinary person recognize one? Why do some meteorites feel unusually heavy? What causes their burned outer crust? Why do certain specimens attract magnets so strongly? And how do scientists calculate a rock's density using nothing more than a scale, water, and a simple mathematical formula? The first clue is weight. Most common Earth rocks have a density ranging between approximately 2.5 and 3.0 grams per cubic centimeter. Many meteorites, especially iron meteorites, are much denser. Some exceed 7.5 grams per cubic centimeter. This means that a meteorite often feels surprisingly heavy for its size. Experienced meteorite hunters frequently describe the experience the same way. The rock simply doesn't feel right. And in geology, unusual observations often lead to important discoveries. One of the most useful tests anyone can perform at home is the density test. The procedure is surprisingly simple. First, weigh the specimen using a digital scale. This gives you the mass. Next, fill a graduated container with water. Carefully place the rock into the container and measure how much water is displaced. This gives you the volume. Then apply the density formula. Density equals mass divided by volume. Or in scientific notation, RHO equals M divided by V. Example: mass equals 480 grams. Volume displaced equals 60 cubic centimeters. Density equals 480 divided by 60. Density equals 8 grams per cubic centimeter. That result would immediately attract the attention of a meteorite researcher. Of course, density alone cannot confirm a meteorite, but it provides an important clue, and in geology every clue matters. Now examine the exterior surface. Notice this thin, dark coating. This feature is known as a fusion crust. It forms during atmospheric entry. As a meteorite enters Earth's atmosphere, it may travel faster than 25,000 miles per hour. The surrounding air becomes compressed. Temperatures rise dramatically. The outer surface begins to melt. Then, within seconds, the molten surface cools and solidifies. The result is a thin black shell covering the meteorite. To trained meteorite hunters, fusion crust is one of the most important visual clues. But appearances can be deceptive. Industrial slag, volcanic rocks, furnace waste, even burned metal fragments can resemble meteorites. This is why scientists never rely on a single observation. Instead, they build evidence, one clue at a time. Now notice these shallow depressions. They resemble fingerprints pressed into clay. Scientists call them Regmaglyphs. These structures form when atmospheric turbulence erodes portions of the meteorite's surface during flight. Not every meteorite possesses Regmaglyphs, but when they appear, they provide powerful evidence of atmospheric passage. An experienced geologist doesn't simply observe holes. They examine the shape, the distribution, the depth, and the geological process that created them. This approach separates scientific observation from simple guesswork. The next test is perhaps the most widely known, the magnet test. Because many meteorites contain iron and nickel, they often respond strongly to magnets. For prospectors and meteorite hunters, this test is frequently the first step. However, magnetism alone proves very little. Magnetite responds to magnets. Many industrial materials respond to magnets. Mining waste responds to magnets. Even railroad slag can produce a strong magnetic reaction. Professional geologists always ask a second question: what additional evidence supports this observation? Because in geology, conclusions require multiple lines of evidence. Another valuable field method is called the streak test. Certain earth minerals leave colored streaks when rubbed against unglazed ceramic. For example, hematite often leaves a reddish-brown streak. Magnetite commonly leaves a black streak. Most meteorites leave little or no visible streak at all. This simple test has saved countless collectors from misidentifying ordinary terrestrial rocks. If a meteorite fragment is already broken, scientists examine the interior. Stony meteorites often contain tiny metallic grains. Many contain chondrules. These ancient spherical structures formed approximately 4.56 billion years ago. They do not occur naturally in terrestrial rocks. Iron meteorites reveal metallic interiors, and after polishing and chemical etching, they may display the famous Widmanstätten pattern, a crystalline structure requiring millions of years to form. No human manufacturing process can naturally reproduce it. Professional meteorite hunters also study the landscape. Deserts are ideal environments for meteorite recovery. Minimal vegetation, limited weathering, excellent visibility. This is why important discoveries frequently occur in Arizona, Nevada, and parts of Antarctica. Hunters often use metal detectors, GPS mapping systems, aerial surveys, and satellite imagery. But regardless of technology, the process always begins with careful observation. Observe, question, test, verify. Eventually, every serious meteorite discovery reaches the laboratory. One of the world's most important meteorite collections is maintained by the Smithsonian National Museum of Natural History in Washington, D.C. Its collection contains tens of thousands of meteorite specimens. Scientists use sophisticated analytical techniques to determine whether a sample is truly extraterrestrial. Scanning electron microscopy, or SEM, reveals microscopic mineral structures. X-ray fluorescence analysis, known as XRF, determines chemical composition. Mass spectrometry identifies isotopic signatures. Together, these methods create a unique chemical fingerprint, a fingerprint that reveals where a meteorite formed, and sometimes even which planet it came from. In April 2012, residents across California witnessed a brilliant fireball. The object exploded with an estimated energy equivalent to approximately 4 kilotons of TNT. Scientists recovered fragments shortly afterward. The meteorite became known as Sutter's Mill. Its study provided valuable information about the chemistry of the early solar system. Then, in April 2023, residents of Maine observed another spectacular fireball. Scientists rapidly identified the impact zone, Within days, meteorite fragments were recovered. Some specimens later sold for more than $25,000 each. Not because they contained gold, not because they contained diamonds, but because they contained information. Information older than Earth itself,